Okay, so this problem says that we have a block A, which has a mass of 50 kilograms, is on rest of a horizontal tabletop. And the coefficient of static friction, mu s, is equal to 0.40. It's a unitless number. A horizontal string is attached to pull over the pulley and to a massless frictionless pulley to a different block, block B. It's a small mass of MB, and it's dangling from the end. We want to know what is the amount of mass, the minimum amount of mass, or just slightly more than the minimum amount of mass for this block to move. Another way to look at this is what is the largest mass that this thing will not move. And that's actually when we see physics problems and they say when it just starts to move, it's really looking at that threshold case. So what is the point where it, right at its limit of moving, where a small light breeze will cause this thing to start to move. So what I have is a couple free body diagrams. Like I normally do with Newton's second law problems, I start with free body diagrams. So my free body diagram for A is going to be a normal force up, a weight force down, a tension force pulling towards the right because of the string, and a friction force pulling towards the left because of the coefficient of friction. All right, and I know for my case, if I were to look at the y components of this, I get my normal force, should probably draw a coordinate system, keep myself in the right coordinates. So in the vertical direction, I have normal up, my weight force down, and I'm not moving because this block is not moving up or down, which means that my normal force is equal to my weight force. In the x direction, I have the tension force to the right and the friction force, mu s, times my normal force to the left. And again, this one does not move because we're just looking for the case where it starts moving, or just the case where it doesn't quite move. What's the most mass we can put on B where it doesn't move? So that's the most tension we can put where we just are right at the limit of static friction, so at the maximum value. All right, which means that my tension force has to be equal to mu s m a times g. Well, I don't know mu s and I don't know t, so hopefully I can get this answer using some other information. But all I did is just said that the normal force was equal to the weight force. The normal force now is over here, so move this to the other side, I get T is equal to mu s times mg. All right, and at that point, we can go no further with block A. So let's look at block B. Probably labeled this one as block A. So block B, I'm going to look and I'm going to say this has a free body diagram. It has a weight force down and has a tension force up. And I'm going to say that my y direction and my x direction are now in these coordinates. So in the x direction, it's the only one I have forces in, I know that mbg, positive value because of my coordinate system, minus my tension force, again equals 0 because this block is just barely beginning to move, or we're looking at the limiting case where it right is at the end, doesn't move. At any rate, its acceleration is equal to 0. So mbg is equal to my tension, and I see that I have tension here, I have that guy there. So let's combine these two equations. It says mbg, so I substituted in for my tension, is equal to mu s m a g. Okay, I guess I actually do know my static friction. That was one of my values. I misspoke earlier. but G cancels out, and I'm left with the mass of B is equal to mu S times the mass of A. So if I know that this is 50 kilograms, and this is 0.4, I can multiply these two together and see that my answer is 20 kilograms. 20 kilograms, so 0.4 times 50 is going to give me 20 kilogram for mass B. So mass B at 20 kilograms with a coefficient of friction of 0.4 will hold, just barely hold, a 50 kilogram mass from not moving, or the 50 kilogram mass will keep the 20 kilogram mass from sliding down if the coefficient of friction is 0.4. So the confusing part on this problem is really just asking, what does it mean to start moving, or the smallest mass that'll start to moving. So it's just slightly greater than 20 kilograms. Just a small light breeze greater than 20 kilograms. Are you accidentally shaking the table? And this thing will start to move. So not that bad of a problem. Two different objects, two different free body diagrams. The first free body diagram, we had both an y and an x. The second free body diagram, we only had a y. Three equations. We solved for the normal, we solved for the tension, and we then solved for mass of B.